Yeah, I think I can start now. So, so welcome to the last lecture of the course. Today we will continue our discussion on CNNs and look at applications of CNNs. And in particular, we will look at applications of unsupervised learning. We will motivate why this is particularly important for medical image analysis, and then we will see how this is done. Okay. So before that, let's quickly review a bit what we did in the last two lectures. So in the first part of, in the first lecture on deep learning, Ender basically gave an introduction on neural networks and described these terms that have been listed here, right? And then in the last lecture, we extended neural networks to convolutional neural networks, and then looked at these ideas of convolutional and pooling layers, some variants of the convolution operator, and then some simple networks for doing image classification, image segmentation, and so on. So like in 5 minutes, I thought I will just recap these things. So a convolutional layer is basically, we define the convolution operator and then we carry out a number of convolutions. And the idea is that the convolution filter, or the weights with which we convolve the image, these weights are learnable parameters of the convolutional neural network. And then once convolved, so once the image is convolved with the convolutional kernel, we end up getting some features or activations, and then we essentially stack these operations. So we get some features, and then we apply convolutions on those features, and then so on and so forth. And at the end, we have some task that we're trying to do prediction for. So that was convolution, and then the other kind of layers that were important were these pooling layers, which are essentially tools for aggregating spatial information. And in particular, what is most commonly used is this kind of max pooling. Yeah. So basically, trying to only preserve the most activated regions, and thus breaking about dimensionality reduction. Okay. And then with already these two layers, we built this simple classification CNN, right? And then we discussed a bit of as to why CNNs are well suited for image analysis. And there were essentially 3 points for this. One was that we have efficient use of weights in CNNs because of this weight sharing property of convolutions, meaning the same kernel actually gets applied throughout the image. So if this is the image and this is the feature map, that is the output of the convolution, each pixel here is connected to only 9 pixels here. So we only have 9 tunable parameters. Whereas if we looked at a fully connected layer, then we would have actually each pixel here would be connected to every pixel in the input image. And that would lead to basically explosion of parameters. That was one point. The other point was this aggregation of spatial features, which is connected to the fact that we do convolutions in this kind of stacking fashion, meaning we have this this idea of deep learning. So we have layer after layer. And what happens is, because of this hierarchy, the initial layers look at only a small portion of the image, and then they end up learning these low level features like edges and corners and so on. And then these features are then built upon as we go deeper into the network. And then we said that this is nice because images themselves have this kind of hierarchy. So the images themselves have more abstract things like organs and so on, which are built upon low level features like edges and so on. So this kind of alignment between the kind of features that naturally exist in images and the way in which CNNs analyze these images is very nice. So this makes CNNs very well suited for image analysis. And then we had this idea of equivariance and invariance towards certain transformations, in particular for translation. And we saw that because of the convolution operator being a shift invariant, we have this translation equivariance in CNNs. And there was a nice question as to what happens when we are pooling. And the idea is that the convolution itself is equivariant, meaning if I just shift the input image, the output will shift by the same amount. But once you add pooling into the picture, then you don't have equivariance anymore. What you get instead is this partial invariance, meaning if you move things around a bit and the change is such that you still remain inside your pooling window, the pooling will anyway pick the highest value. So if the thing gets shifted a bit with the highest value remaining inside the window, then you still end up picking the same activation, right? So you have invariance to small translations due to pooling. And then finally, we had these different variants of the convolution operator. So 3D convolution, one-by-one convolution, dilated and transposed convolutions. And then we used some of these to build a segmentation network. Okay, so this was like a quick, maybe 5-minute recap of what we saw before. Yeah, again, if there are questions, please feel free to stop and ask. But otherwise, I will just move on to the contents of today. Okay, so today we are going to look at unsupervised learning. Okay, and we will begin by first pointing out the differences between unsupervised learning with supervised learning. So all the things basically that we discussed in the last lecture were supervised learning problems. So we will see how unsupervised learning is different from that. And then we will look at the applications of unsupervised learning. So what I mean by technical applications is applications in terms of method. So what have been listed here are still like are methods, but they fall within the umbrella of unsupervised learning. Okay. Whereas on the right, what we have are like true applications for medical image analysis. So typically, what we will see is that we will look at unsupervised learning, and then we will pick one of these technical applications, let's say representation learning. And then we will look at the applications of representation learning for example, dealing with annotation scarcity or for lesion detection or something like this. So this is going to be kind of the flow of today's lecture. Okay. So let's start with looking at supervised versus unsupervised. So what is supervised learning? Supervised learning is we are given a data set of pairs. So we always have X and a corresponding Y. So typically in our case, X is an image and Y is a classification label, or it's a segmentation map, or it's like the high resolution image corresponding to the low resolution X, or something like this. X and Y are always paired, and we have a data set of these. And then what we can do is a number of applications like this. And how we do it is basically we have a 3-step approach. As a first step, we need to design a CNN architecture that takes X as input and outputs Y. Okay, and this basically means we have to design what we have to kind of plug and play. We have to select the building blocks that we know. For example, convolutional layers, max pooling layers, upsampling layers, and so on. So we have to select what combination of these layers do we want to plug together to describe a mapping from X to Y. Okay, so that's the first step. That is called the CNN architecture. Once we have that, then that CNN will have some learnable parameters theta. Okay, and now we need to adapt these parameters. We need to optimize with respect to these parameters. And for doing this, we need to define a loss function. So when we feed in some image X and these thetas are randomly initialized, there will be some prediction Y. Okay. Now, usually this prediction Y will be very different from the target prediction that we have in mind. But we know exactly what this target prediction is in the case of supervised learning. So we define some kind of loss measure that measures the discrepancy between what the prediction is right now and what we would like the prediction to be. And then we optimize with respect, we minimize this loss function with respect to the parameters of our CNN. So this is the general recipe of supervised learning problems, right? What changes? Okay, so what's important to note here is that for these methods to work well, we need typically to have access to a large data set of labeled images. Okay, so if we don't have a large number of labeled images, then this mapping that we have here may overfit to the few labeled examples that we have, meaning it will actually give us good performance on the few labeled examples that we have. But then when we go ahead and test it on new images, we will not get good performance. And the reason for this is the initial training dataset size was not large enough. And this happens all the time in medical image analysis, because the labels Y for medical images have to come from radiologists or clinicians or something like this. And these people usually don't have the time to sit down and annotate 1,000 images or 10,000 images or something like this. Usually we have access to like tens or in the best case hundreds of labeled images. So this is a kind of a big bottleneck as far as performance of CNNs in medical image analysis is concerned. And therefore, what people try to do is people try to use unsupervised learning, where one says, please don't worry about the labels. Just give me a lot of data. Just give me a lot of images. Okay, and this can be relatively easier to obtain. So images are being acquired in the hospital every day, and then if we are able to sort out anonymity things, like we can make sure that privacy is preserved, then these images can be relatively straightforward shared from the hospital to someone who is building machine learning algorithms. Okay, so we have a lot of images, but what can we do with this? Can we do something useful with this? And unsupervised learning says, okay, let me try to understand the underlying structure of these images. Okay, so this is a very kind of vague statement, but it allows for different interpretations. So a few interpretations are, what one can do is one can reduce the dimensionality of the images. So let's say we start with images that are 100 by 100 pixels. So now we have 10,000 dimensional images. Now, usually what happens is that this representation of images, this pixel representation of images is good for the human visual cortex, which is, evolved over so many years to understand this representation. But actually, there's a lot of redundancy in this representation. There's not actually so many dimensions which are relevant for algorithms to process these images. Okay, for instance, in a toy example here, we have, let's say, some data, and let's say we don't know these triangles or circles. Okay, these are just some data points, and we have 2D data in this case. So we just plot it on a XY plane, and this is the data, and we see that there is a lot more variance along this direction as compared to orthogonal to it, right? So if instead of representing each point with a X coordinate and a Y coordinate, if we changed our representation so as to represent each point with its coordinate along this axis, then we could represent all the data points with just one number instead of two, and still preserve most of the information in the data. So all these points will collapse on this line. But if we then wanted to do something like classification, we would still be able to threshold the coordinate here, and all these points will get mapped to one class, and these points will get mapped to another class. So the point is that in a totally unsupervised way, without knowing the class of any of these points, there is still a possibility to do this dimensionality reduction of the data, which may further help in downstream applications. Okay, so some examples of this, some methods which try to do this are principal component analysis, which is like a linear way of dimensionality reduction. A CNN-based approach to do this is what are known as autoencoders, which we will talk about a bit later. But autoencoders are essentially nonlinear ways of doing dimensionality reduction. Okay, So that's one way of doing unsupervised learning. Another way is that one can say, if I'm given some data and I just plot the data in whatever dimension it exists in, can I try to find if there are some clusters in the data? Okay. So here again, okay, these points are marked in different colors, but if we assume all these points to be just black, okay, and then we try to find if if there are naturally occurring clusters within this data based on some distance metric that we come up with, then this can be useful, because if we are able to say that all these points belong to one cluster that is different from these points, that is another cluster, then we have already done an unsupervised classification task without having any knowledge of, what was the label of this point versus this point. Just based on unsupervised clustering, we were able to do this classification. And some methods for doing this are like k-means clustering, which I think may have been covered in the earlier lectures of this course, or GMMs, Gaussian mixture models. Okay. So the first two things that I mentioned here, this was just to give you a taste of, that unsupervised learning is not totally hopeless, that, that there are meaningful things that we can do having access to only images without any labels. But going forward, in this lecture, what I would like to do is focus on the next two applications that I will mention. So the first one is representation learning. So this is, we have some image which is 100 by 100. And now we want to represent this image in a different way, which makes things easier for downstream analysis. And we will make this more concrete as we go forward, but this is kind of the general idea, that we want to go from this pixel-wise representation to some other representation. And this is something that we can do only having access to images without any labels. And a common way of doing this is what is known as self-supervised learning. So, it's kind of between supervised and unsupervised learning, right? So it's supervised, but we will see. We will see. It's self-supervised. So the images themselves tell us how to supervise the learning problem. But we will come to that. And then the last application that I want to mention here, or the last interpretation of what it means to understand the underlying structure of the data, is estimate the probability distribution of the data. So again, we will look at this in a lot of detail as we go forward. This goes by the names of density estimation, probability density function estimation, or generative modeling. Okay. So now I'm going to start with this. Maybe I will stop for like 30 seconds to see if there are any questions at this point. Okay, seems like there are not. Okay, so let's start with self-supervised learning. So the main idea is to convert the unsupervised learning problem into a supervised learning problem. Okay, and for supervised learning problems, we know that we need pairs of inputs and outputs that we can then ask the network to learn the mapping between. And in self-supervision, we basically come up with pseudo outputs. Okay, so what we can do is, for example, we can take an image as input, and we can ask the network to output the same image. Okay, so now there was no output to begin with, but we said that we construct a self-supervised task, which is to reconstruct the same image that was the input. Okay. Or we can add noise to the input image. So now the input is a noisy image, and we can ask the network to output the clean image. So now we have designed a denoising task, again, without access to explicit labels from outside. Or we can blank a part of the image. Okay, so we select a certain area of the image, we just set all the pixel values to 0, and now the network has to, based on the other pixel values, predict the whole image. And this is known as an in-painting task. Okay, so again, this is an example of a self-supervised task. Or we could rotate the image. So we give the image to the network and we ask it to predict, okay, now the image has been rotated by 0 degrees, and then we rotate the image by 90 degrees, and then the network has to predict, okay, it has been rotated by 90 degrees, and so on. So again, we are kind of, in all these cases, kind of heuristically coming up with input-output pairs, and then asking the network to learn the mapping between these inputs and outputs. That's the main idea of self-supervised learning. Okay, so concretely, some examples here. So again, so autoencoders, basically autoencoders meaning you encode yourself to some representation and then get decoded back to the same value, thus auto, right? So you get start with X, which is some image. So okay, we have access to images only, right? So we take that image that we have access to, we pass it through a model, and then whatever the output of the model is, we train the model to be such that the output is similar to the input. So this L can be, for example, a pixel-wise L2 loss between the reconstructed image and the input image. Now, if you just do this like this, there's a chance that the network may just learn the identity mapping, right? All the convolutional layers may be just identity mappings. Each one of them can be identity maps, and therefore the output will be the same as the input. But this will not be very useful. So what we then say is that actually we will force the network to go to a low dimensional space. So we will make this encoder such that, for example, we will construct it with convolutions, max poolings, and so on, such that Z is a lower dimensional entity than X. And then we will try to decode X hat from this lower dimensional entity. Okay. So for example, if this is 100 by 100, and we make Z to be 10 by 10, then all the information about these 10,000 dimensions in the input has to be squeezed into the 100 dimensions in the latent space. And then the decoder, based solely on the information in these 100 dimensions, has to reconstruct the 10,000 dimensional information. Okay. So this then becomes like a low dimensional representation of the image, and therefore we call this representation learning. We are learning a new representation of this pixel-based representation. Yeah. So this is what autoencoders do. Then we can have context autoencoders, because we are going to blank some part of the image and we are going to feed it through this mechanism and ask for the whole image. Okay, and they're called context because now it's easy to predict the things going on in these parts of the image, although they also have to be squeezed into through this bottleneck. But the other challenge is to predict what's going on here based on the context, right? So that's context autoencoders. And one way of viewing this is that this is a corrupted example of the image. This is a particular type of corruption that we have chosen that was proposed in this paper, but there's nothing stopping us from choosing other types of corruptions. So for example, we can just add Gaussian noise to the whole image. We won't do this blanking part. We just add Gaussian noise, and then we ask the autoencoder to reconstruct the image without the Gaussian noise, and then we would be doing denoising autoencoders in the more traditional sense. But we need not even stop there. We can just come up with whatever corruption mechanism that we think is suitable for our application, and then we can train a network to undo that kind of corruption. Okay, so that's another way of doing self-supervised learning. Then this is the rotation prediction task that we saw before. So you can feed the image and then ask this class, you can just randomly assign this class to be something, 1, for example. And now we have flipped the image 180 degrees and we can say, okay, this is class 2. And we can choose whatever number of classes we like. And the idea is that after training on these self-supervision tasks, these networks here will learn something useful about them. image. In particular, the representations that come out of the encoder will be useful for some other tasks that may be of interest. The self-supervision tasks are, at the end of the day, just a means to an end, right? We are not really interested in the self-supervision task. We are actually interested in, I don't know, some kind of classification or segmentation or something like this. But what we want to do is we want to still use this self-supervision to leverage unlabeled data for which we do not have labels for the task of interest. We want to leverage that kind of data to learn meaningful representations. Okay. Yet another type of self-supervision is this kind of prediction of relative patch location, meaning I will feed an image this time with 2 patches and ask the network to predict the location of this patch relative to this patch. So now it has to, over the training periods, it has to understand that ears always go on the top right of the eyes or something like this. And so these were, like, I would say, all these things that we talked about so far. So autoencoders, context autoencoders, denoising autoencoders, rotation prediction, relative patch location prediction. These all go into like one basket of self-supervision tasks where we define some kind of input and output pairs, and then train a network to do that. Contrastive learning is I would put them into a different basket of self-supervision tasks. Okay, and the idea of contrastive learning is to contrast different augmentations of the image. So what is augmentations? First of all, augmentations are different transformations of the image. So what we do is we have this image and we transform this image in different ways. So in this transformation, we have cropped the face of the dog and we have changed the color. Okay, and in this transformation, we have cropped the legs and then we have changed the background. So these two are known as two different augmentations of the same image. And what we are going to do for self-supervision is that so this is again an encoder that we were seeing before. Okay, so we always have the encoder and then some classifier. So here again we have some encoder. It's just rotated 90 degrees because I was too lazy to make a picture of my own. I took the picture from the paper. So we feed these two augmented versions through the feature encoder. And then we get some representation. So these are the Z's that we were talking about before. Okay. And similarly, we take an image of another class. Okay, so this is an image of a dog. This is an image of a chair. We make two augmentations of the chair. We pass them through the encoder. So what has happened so far is that we started with 2 images. We made them into 4 images, which are, 2 of them belong to this one and 2 of them belong to this one. And we end up with 4 representations. And now what we are going to do is we are going to ask that this representation that we have here be different from these representations, because this representation belongs to a dog and these representations belong to a chair. So we're going to repel the representation of one class from the representations of the other classes. Okay, as well, we're going to attract the representations of the same class, because we know that ultimately, although they look like different images here, they belong to the same class. So we would like these representations to cluster together. So we define some kind of loss function that minimizes the distance between these representations, and similarly these representations, because they also belong to the same class. But it maximizes the distance between this representation and this one, for example. Okay, so we have to define what are known as positive and negative pairs of images. So we say that images coming from the same class but different augmented versions are positive pairs, whereas images coming from different classes are negative pairs. And then we would like our representations to behave accordingly. So again, essentially we have come up with some heuristic way of imposing some domain knowledge, and then we are training a network to behave according to this knowledge. Cool. And what we discussed so far was really a small, although we discussed a few different methods, this is far from being exhaustive. So there's this idea of self-supervision has become very popular in the past couple of years. And yeah, there are a number of papers, and already there are reviews of these methods, which shows you that, a lot of things are being done at the same time. So yeah, this I list here just in case you're interested and want to have a look. And now I want to talk a bit about what we do with these representations. So we said that we are going to use self-supervision in order to learn quote unquote meaningful representations. Okay. So how do we know whether the representation is meaningful or not? So what we are going to do is we are going to think about any one of the self-supervision methods. Let's say we do the autoencoder. Okay, so we train an encoder and a decoder, and the encoder is going to output some small low-dimensional representation of the image. Okay. Now, once we have trained this autoencoder, we are going to throw away the decoder, and we are going to say that this Z is the learned representation of the image. Now, we're going to add a new neural network here, a task-specific neural network that is going to output a Y which is defined according to the task that we have in mind. So if you want to do segmentation, this Y would be of the same size as the image, but this would actually be in the space of image segmentations. And we are going to fix this feature encoder, this representation learner, and we're only going to adapt the parameters that are in this neural network. And to do this adaptation, we are going to use a few labeled examples of X and Y. So now we are working in a scenario where we had a lot of unlabeled examples, a lot of unlabeled images that we could train the autoencoder on. Then we threw away the decoder, we fixed the encoder, and we are now training this task-specific CNN using something like 10 labeled images. Okay, and what we would have had to do otherwise was we would have had to train the whole network using only these 10 images. But now we are saying we were able to leverage the unlabeled data set of 1000 images, for example, to learn this encoder, fix it, and learn only the decoder with the small number of labeled images that we have. Okay. Now, assuming that the self-supervision task, okay, whatever we chose, that self-supervision task had some similarity to the actual task that we are interested in, the extracted features will be relevant for both tasks at the same time if the tasks have some similarity. Okay, and if this is the case, then these extracted features will be useful for doing this task as well, and thus we have achieved our purpose. That's kind of the broad idea. I think it's a good time to stop, and then I'm sure there must be some questions at this point. Let's see, there's something in the chat. It's freezed. Oh, wow. Is it okay now? Oh, okay. How long was it frozen for? Is it? Okay.
A few seconds.
Yes. So, yeah, I don't know what got skipped, but in any case, yeah, if there are any questions or comments or, why is this useful? When do people do this? Whatever. Yeah, it will be nice to maybe talk about that before we move to the next block.
I have a question to this slide.
Yeah.
Is there a way to determine if your self-supervised task is enough related to the task of interest, or is that just experience?
Yeah, that's an excellent question. As far as I know, there is no principled way of doing this, of guaranteeing that the task that you chose is relevant for what you need in the end. So, yeah, it's a matter of experience and looking at what other people have done and what seems to help and so on. So there's definitely work to do there to make it more reliable. Yeah.
So in practice, you would just try and see if you could get good results with this, and if not, you would try something else.
Yes, exactly. I mean, you could try to reason about, okay, if I'm trying to do image segmentation, maybe my self-supervised task should have something to do with segmentation labels. You can make some informed, assumptions like this. But at the end of the day, it's still based on, there's no like proof that this kind of task is going to correlate well with the task of interest. Yeah.
Okay, thank you very much.
Mm-hmm. Okay, so if there is nothing else at this point, let's move on let's move on to the next one. So what we have done so far is we started by looking at the difference between supervised and unsupervised learning. And then we started looking at what we can do with unsupervised learning. So we only briefly covered dimensionality reduction and clustering because I believe that most of you already are familiar with these ideas. But just to recap that, it's meaningful to try to do things only with unlabeled data. And then we talked about representation learning, and in particular self-supervised learning. And then we saw that one of the applications of representation learning is to deal with annotation or label scarcity, which is quite common in medical image analysis. Okay, so now next we are going to move. Okay, I had this other list. So again, it's the same that we discuss these things briefly and this in a bit more detail. And now we are going to talk about estimation of probability distributions. Okay, so I think it's important to motivate this. So if we do some kind of a visual exercise, again, let's look at our case of 100 by 100 images. Okay, so images are these points in 10,000 dimensional spaces, like in a 10,000 dimensional space, right? But now, okay, so this is really a vast space, right? 10,000 dimensions. Okay, now think of a randomly chosen point in this 10,000 dimensional space. Okay, you just roamed around, and then you sat at one point and you said, okay, this is the point I want to select. Now, most likely, this point will not be what you consider a good image or a plausible image. I hope this is key to understand that this space is really big, and that most points in the space are going to look like the picture here. What points in that space actually look like an image have to conform to certain requirements, that you need to have really some kind of structural correlations within those images for those images to qualify as good images. Okay, so for example, if I'm considering the space of images of the brain, there are really very particular correlations between pixels that would qualify a member of this 10,000 dimensional space to become a member of the space of brain images. Okay, and the task of density estimation or distribution learning is to somehow characterize this set in this big space. We want to characterize the subspace which such that in this subspace all the points are going to look like plausible brain images. Okay. So this is kind of the task of density estimation or generative modeling or distribution learning and so on. Okay. Now, we are going to look at two ways of doing distribution learning, an explicit way and an implicit way. Okay. So what do we mean by this? In the explicit way, we are going to want a model CNN because the class is about CNNs. But the point is that this model should take as input a data sample, so some image of the brain, and it should output the probability density value at that location in the space in which the images lie. Okay. So if this will be an image of the brain, we would like this value to be large. And if this is a random noise image, then we would like this value to be low. Okay. And given a data set of 1000 brain images, we would like to adapt these parameters theta such that the aforementioned behavior is obtained, that for the images that we are given, we get high values of the density function, and for other images which are not good brain images, which are just noisy images or brain images with some lesions or brain images with some artifacts, for all these types of uncommon images or all these types of images that were not part of the training data set, we would like the output to be low. Okay, so this is how we want to train the model. Okay, again, it's like, it looks like an input output problem, right? So we have it almost sounds like a supervised learning problem, that we would have X, we would want a certain Y, and we would like to optimize with respect to theta to get such behavior. The problem is, however, that we don't know what the p-value should be. We just know what should be high and what should be low, but we don't know exact values so that we can define a loss function like we could do for the supervised learning problems that we talked about. Okay, so how can we then do this? We will look at that. And then the other way of unsupervised learning of data distributions is an implicit way, meaning we never have a function like this. Okay, we never have a quantification of the density function. What we have instead is a mechanism where we can feed in some vector which is sampled from a known distribution. So we should think of this, I think it's easiest to think of it as sampling from a distribution of Gaussian noise. So Z can be a vector of 100 elements, where each element belongs to a univariate Gaussian with 0 mean and 1 standard deviation. Okay. So this Z will be a 100-dimensional vector of noise. And we want this model to be trained such that when it gets fed with an image which is just noise, or with a vector which is just noise, it outputs an image which actually looks like a brain image, which actually looks like an image which is similar to our training data set of unlabeled images. So what has happened now is that this model implicitly knows what good images look like, because it's always outputting images that look like good images, whereas the input has no clue about the images themselves. The input is just noise, but the model implicitly knows what images are good images. In other words, the model implicitly knows which areas in the image space have high probability values, but it knows it implicitly. So this is the other type of data distribution learning. Okay. I almost want to take a short break right now. Yeah, I think I will do this. So let's take a break for maybe 10 minutes and then reconvene and continue from this one. So let's meet at, okay, so let's restart. So, okay, we said that we want to talk about density estimation. And we said there are two ways of doing this broadly, explicit and implicit. So let's start to talk about the explicit way of doing it. So we get a data sample and we want to train a model such that it outputs a high value if the data sample belongs to the training data set, which consists of unlabeled images, but all unlabeled images are, we know, good images. They are all images of the brain, for example. So what does this look in 1D? In 1D, we have some data points that are just plotted on the x-axis here. Okay, so in high dimensions, there would be images that we get, and if we had some way of visualizing the high dimensional data, it would be, we would just make one dot for one image, and like that we will have these dots. And the goal of density estimation, explicit density estimation, is to make a function like this, which is the probability density function of that corresponds to this data, meaning it has high values when we have a lot of samples and low value when we have low or no samples. Okay, and before we go into how do we go about building this function from the data itself, let's look quickly as to how this function can be useful once we have it. So one use case for this would be that if after training this data, we get a new data point here, then we could ask the question whether this data point is real, or sorry, normal or anomalous. Meaning, is it like the images that we saw during training, or is it different from those images? So, and then what we could do is we could evaluate this function at that point. And if we get a low value, then we say, okay, this point does not look like the points that I saw during training. How can this be used for medical images? Is that if we have a data set which consists of images which we know are all images of healthy volunteers. Okay, so all these people do not have any lesions in their brains. They all have different structures, like they have structures, and the structures may differ, meaning differ because there is natural variability in the population. Someone's hippocampus may be slightly larger than the other one. So the shapes may differ, but all this variation is just naturally occurring variation in healthy brain images. Then if we have such a data set, we could try to learn the probability distribution of healthy brain images, which in 1D would be the same as learning this function, right? So we are just looking at this in 1D. In high dimensions, we cannot visualize this. But the point is that we should have high values where we have healthy brain images. And we try to learn this function from a data set of a lot of healthy images. And then given an image like this, which consists of some lesion, we could ask exactly the same question. We could evaluate this function at the test image. And then if the output value is low, then we say that this image probably is different from the images that I saw during training. In particular, like further, what we could do is we could train this curve on image patches, and then we can, for the test image, we can ask for each image patch the same question, whether each patch is healthy or anomalous. And all these patches will look like the patches in the healthy images, whereas patches in the region where there is a lesion will not look like that. So we will get a low output value from the model at these points, and then we will be able to identify the lesion from the image. In other words, what we have done is we have done lesion segmentation, but we did not have lesion and segmentation pairs for training this model. What we had was just a data set of healthy images, and we were able to then use this data set to come up with a model that could now segment lesions from lesion images. Okay, so this is one application. Another application is what is known as image restoration. So again, in this case, we assume we have access to unlabeled data of what are known as fully sampled brain images. Okay, so this is some MRI related term. For what we mean by fully sampled is that, okay, let's see. So if you know a bit about MR imaging, it's basically, the idea is that it takes a long time to acquire the image. Okay, the image is acquired in so-called K-space, which is a Fourier space. That's not relevant, but it's acquired in a different space. And if we try to acquire the image fully, meaning if we try to acquire all the points in the K-space, then it takes a lot of time to acquire the image. But then what we get at the cost of this time is that a very good looking image. But often we don't have this time, especially for patients, you don't want to keep them in the scanner for a very long time. So you acquire only part of the case space. And then what that looks like in the image space is that you get these kind of aliasing artifacts. Okay. So now what we would like to do is we would like to acquire the image in a low amount of time, get this image with artifacts, and then somehow remove the artifacts from the image so that we would have the best of both worlds. We would not have spent a lot of time in the scanner and we would still have a good image. So how we do this is that we assume access to fully sampled images, a data set of fully sampled images. So a data set of artifact-free images. We learn the distribution of those images. Now, when we get a new image like this, which is acquired in low time and has an artifact, this will have a low value under this probability. So what we will do is we will find the gradient of the probability density function at this value, and we will change the image such that the probability density value increases. So we will move along the gradient of P of X. What that will end up making the image is that will actually say, okay, if you want to increase the PDF value, you actually have to move the image along this direction. And at the end of this optimization, we will end up with a restored image, which will actually have a high value under the PDF, but which would have come from the artifact ridden image that we started with. Okay, so this is yet another application of what we could do once we have built this kind of function here. Okay, all right, so that's the motivation. And now let's try to look a bit into the details of how we try to do it. How do we model the data distribution? And in particular, what we will look at is this type of models called variational autoencoders. So we will look at one type of model for implicit, one model for implicit distribution learning, and this is VAEs. And then, sorry, I'm very sorry. So we'll look at one model for explicit distribution learning, and that is VAEs. And then later in the lecture, we'll look at one model for implicit distribution learning, and that will be generative adversarial networks or GANs. Okay, so VAEs, what are VAEs? They have the word autoencoder in them, which is because we have this encoder decoder like structure that we saw before. But actually, the theoretical basis of VAEs is quite a bit different from the autoencoders that we saw before. Okay, so we will keep this picture here, but now let's dive a bit into the theoretical side of VAEs, and then we will try to reconnect it with the autoencoder picture. Okay, so so I would recommend paying a bit of extra attention for the next 10 minutes or so, because this is the only part of the lecture that's a bit math heavy, but I think it's useful to understand this. Okay, so now VAEs are what are known as latent variable models. So what it means is we have two random variables in our model. One of them is the observed variable X, meaning the images themselves. So these are the images, these are the random variables that we observe samples of, right? So if we get images from the hospital, these are all different samples of this random variable. Okay. Now, in a latent variable model, what we say is that we believe that the images that we observe have some kind of hidden representation. Hidden meaning we do not observe that representation. For instance, we could say that brain images can be described in a different representation, which consists of, for example, the size of the hippocampus, the amount of gray matter in the brain image, the age of the person, the size of different tissues, and so on. So this is like more abstract information, which is not the same as the pixel level information. But we don't have access to this hidden representation. Okay, so those hidden representations or latent variables are what are known as C. Now, in a latent variable model, we can write down the P of X or log of P of X as the marginal. So we can look at the joint distribution of P of X and Z, and then marginalize out Z, right? So the joint distribution by chain rule becomes P of X given Z, P of Z, and then we integrate out Z So we are left with just P of X. Okay. Now, what we want is a model for this, right? So we want to tune theta such that P of X has large values for x's that are good images and low values for x's that are not good images. Now, here we have expressed this P of theta in terms of this integral, right? Now, this integral is over z's. The z's are low dimensional as compared to x's. X's are, let's say, 100 by 100, so 10,000 dimensional. Z's are, let's say, 100 dimensional. But it turns out that it's actually not practical to integrate over a 100-dimensional space. Okay, this is just not computationally possible. So we need to find another way to do this. We cannot use this kind of representation here. Okay, so to get around this, in VAEs, what we do, and this is where the word variational comes into play, we do what is known as a variational approximation. Okay, so what is this? Now this will look like a bit of a detour, but stay with me for a couple of slides. So we start by looking at the posterior distribution. So posterior distribution is P of Z given X. Okay. And we write down with Bayes rule this in terms of the likelihood term X given Z, the prior on the Z's divided by P of X. So this is the term of interest, but now temporarily we are looking at this posterior. You will see why. First we note that we first said that P of X is intractable, meaning we cannot compute it because of this integral over z's. Now P of Z given X also depends on P of X. So P of Z given X is also intractable because of the same reason. So we do not have a way to compute this either. Okay. So in variational approximation, what they say is that let me introduce a new distribution, Q phi of Z given X. So it's the distribution over the same random variable given the same random variable. So both of them are Z given X. But this is a different distribution with a different set of parameters. And we say that we want to use this distribution to approximate this distribution, which we said is intractable because of the integral involved in this term. Okay. So we have the true posterior, we come up with this approximate posterior. That's the basic idea. Now, we want to construct this approximate posterior such that it's similar to the true posterior. In order to do this, we need to define some kind of discrepancy measure between two distributions so that we could then minimize that. And what we choose is what is known as a KL divergence, or the Kullback. Okay, this is not good. It's something like this. Kullback. It's a difficult pronunciation. So it's the KL divergence, and it's something that measures discrepancy between two distributions. So now here we have the density functions corresponding to these distributions, and we would like to minimize the KL divergence between them. Okay. Now, one property that we should know about the KL divergence is that it's a non-negative quantity. So if the two distributions match exactly, meaning at each point Z, if they evaluate to the same value, then the KL divergence is exactly 0. In all other cases, it's strictly positive. Okay, so overall, it's a non-negative quantity. And it's defined like this. It's defined as the expectation over the first distribution of the log of the ratios of the two densities. Okay, and the log of the ratio splits as the difference between the logs. Okay, but essentially we are looking at the ratio of the densities, taking the log of that, and then taking the expected value over one of the distributions. That's how the KL divergence is defined. And remember, we want to minimize the distance between these two distributions. So we are minimizing the KL divergence. So whatever 2-3 steps we do now, we will come up with the formula that we would like to minimize also. Okay. So first step is we are going to look at this true posterior, and we are going to write it down using Bayes rule. It's just Bayes rule, and the log means that the multiplication becomes addition and the division becomes subtraction. So that's just that. And now we have our quantity of interest showing up here. This is the thing that we are doing all this hard work for, right? So we want to ultimately have something which relates to this. Okay, so this is just KL divergence definition and then Bayes rule. And now we are going to rearrange the term. So we are going to use the KL divergence. We are going to bring it on the right-hand side. We are going to keep log px here. So log px minus the KL divergence between the two posterior distributions. And everything else goes on the other side, so their signs change. So then it's expectation with respect to Q of these three terms with appropriate signs. This is just rearrangement of the terms. Right? Now, because of what we said before, that the KL divergence is a non-negative quantity, even if we have no way to compute this, we know that this is always going to be 0 or more than 0, which allows us to put a bound or an inequality sign between this term here and everything that's on this side, right? So exploiting that fact, we get log px is always strictly greater than or equal to whatever we have on this side. Okay, this is just what we had here. So this first term is log expectation with respect to q of log px given z. And then these two terms combine, in the KL divergence formula to get a KL divergence between two different distributions. So here the KL divergence was between the approximate posterior and the true posterior, whereas here the KL divergence is between the approximate posterior and the prior on the z's. But this is just what comes out of the little algebra that we did here. But what is important is that we have a formula, or we have a bound for log px. So we said we would like to maximize log px. So for all, because we have a data set of good images, we would like px to have high values. So we would like to change theta or adapt theta to give high values to all the images that we have. But we said we cannot do this because of the integral over z's. Now what we have another definition. We have a lower bound to log px, but this is something that we can maximize. Okay, and notice that if something is a lower bound, so if the thing on the right hand side is a lower bound with respect to log px, if I maximize the lower bound, I'm actually pushing log px also up. Okay, so it actually makes sense to maximize a lower bound. So what we do in VAEs is we maximize the thing that we have here, and therefore this is known as the variational lower bound or the evidence lower bound. So variational because we use this variational trick. Variational meaning every time we do some approximation and then make the approximation using some optimization, it's known as a variational approximation. And evidence lower bound because log px is also known as evidence, and now this is a lower bound to the evidence. So these are just two names for the quantity on the right here. And in VAE, we are going to maximize this quantity. Okay, so just a recap, we started with wanting to maximize log px. So, okay, I hope it's clear that maximizing px and maximizing log px are one and the same, because log is a monotonically increasing function. So whether we increase px or whether we increase log px, it's qualitatively similar. Okay, so we want to maximize log px, but we cannot do it because of this integral. And therefore, we introduce this approximate posterior and we come up with this variational lower bound. And this is what we are going to maximize instead. Okay, I think that's quite a bit. So I'm sure there are some questions, or I hope people are not completely lost. So if someone could just comment or just something, it would be a bit of it would be nice. Okay. Okay. Sounds like it was okay-ish. Okay, so yeah, anyway, so if there are questions, again, I would like to reiterate this, so just interrupt me at any time. So we came up with this bound, yes, and now we want to see how to implement this in practice, and this is where the autoencoder picture comes back again. So we want to maximize this quantity. Okay. So this quantity consists of two terms. We have, if you look, we have three distributions in this quantity. One is p theta z given x. Another one is p theta x given z, q phi z given x, and p theta z. So basically there are three distributions. And what we are going to use, what we are going to do is we are going to use neural networks to model these distributions. So in particular, we are going to use an encoder network to model the distribution of z's given x's. We are going to use a decoder network to model the distribution of x's given z's. And we are going to fix the prior on the z's to some reasonable distribution. So in particular, what is commonly done is that this distribution, q phi z given x, is modeled as a Gaussian distribution. So a Gaussian distribution is defined by its mean and a covariance matrix. So we have a mu in the z space, which is a function of x and depends on parameters phi. This is modeled by a neural network, which gets as input x's and has parameters phi. And another neural network is going to output the covariance matrix based on an input x and parameters phi. And these together will define this distribution in the latent space, this conditional distribution in the latent space. Similarly, we will have a distribution here, which we will also typically model as a Gaussian distribution. So again, we need neural networks to output the mean vector in the X space and the covariance matrix. And then the prior in the Z space is usually fixed to like a zero mean, identity covariance Gaussian. And then we have to basically plug this into the formula that we have here. So we want to maximize this. So we want to minimize the negative of this, right? So we want to minimize this guy. And the parameters are theta and phi, which happen to be the parameters of our neural networks. So at the end of the day, in CNNs, it always boils down to this. You come up with some loss function, and you make sure that the loss function is differentiable with respect to the parameters of your CNN, and then you minimize the loss function, or if you want to maximize it, you minimize the negative of it. So yeah, the same is done here, and then at the end of the day, we have a model. Once we train it with a lot of good images, a lot of brain images which are artifact free or something like this, whatever good means for our application, what we can do is, given a new image, we can pass it through this trained neural network and evaluate this quantity. Okay, and this quantity is going to be an approximation of log px, and this is then going to allow us to do all the applications that we talked about. So we are going to be able to say whether this red point has low log px value or high log px value. So in other words, we are going to be able to detect anomalies. Then this is what was done in this paper recently. And we are going to be able to also follow the gradient of p of x to improve the image, to remove artifacts from the image. And this is again what was done in this paper a couple of years ago. So yeah, so that's the thing that I wanted to discuss about explicit learning of data distributions. So we only covered variational autoencoders. There are other things that can be done here, but I think it's good to have a taste of yeah. Instead of just mentioning a lot of things, I just wanted to go slightly deep into one of those and talk about that. Yeah. So next is a summary. So we have we discussed about representation learning. So we discussed about self-supervised learning before, and we saw that it could be used for dealing with label scarcity. And now in the last 20 minutes or so, we discussed about variational autoencoders, and then we saw that once we have such a model, which is learned completely unsupervised, we were able to use it for anomaly detection or for image restoration. So here, we saw an example where we were restoring the image, meaning we were going from an artifact-ridden image to an artifact-free image. But this could be anything, right? So this image could be, for example, a noisy image, or it could be an image with some other types of artifacts, so motion artifacts. This is also kind of the nice thing of unsupervised learning, that once we have a model that knows what good images look like, we can start with any type of bad images potentially, move in the direction where the density increases, and we will be able to convert whatever type of bad image we have into the corresponding good image. So the generality of these methods is really a very strong point here. Okay. Okay. So this is what we have so far, and then in the last I don't know 15 minutes or so, I would like to talk about the implicit way of doing distribution learning. So again, I would like to stop for maybe half a minute and then see if there are comments or something like this. Also because I need to catch my breath. Okay, okay, okay. So yeah, let's talk about the next topic. So this is the implicit way of doing learning of data distributions. So what this means again is that we do not have a model which outputs the value of p of x or log p of x. Instead, we have a model that takes as input a sample from a known distribution, for example, a noisy vector, and then implicitly knows what the distribution of brain images looks like. And it uses this implicit knowledge to transform this noise vector into an image that looks like an image of a brain. Okay, so here we won't go into as much detail mathematically. We will try to get a more intuitive understanding of how GANs work. And then, yeah, I will only briefly talk about the mathematical basis. But the basic point is still the same, that we still want to have a model for the probability distribution. And we want to minimize some kind of distance between the true probability distribution of which we have samples, right? Because we have images from the true distribution. So we would like to minimize the distance between the true distribution and the model distribution. And in VAEs, we minimized, it turns out we maximized the likelihood of the data. In GANs, we will minimize what are known as F divergences. So this is like, we talk about loss functions in supervised learning, right? So we talk about L2 losses or cross entropy losses and, dice loss for segmentation and so on. So similarly, we have a bunch of divergence measures that define distances between probability distributions. And the difference between VAEs and GANs is that they minimize different loss functions at the end of the day. Okay. What happens in GANs is that, okay, we have this, what is known as a generator network. So it takes as input some noise vector, and it is supposed to map something, output something that lies in the space of images. Okay. And what GANs also have is that to be able to decide whether the output belongs to the set of good images or not, they have a new neural network which acts as a classifier. So the job of the discriminator, this new neural network, is to say whether its input is a real image or it's an image generated by the generator. So what happens is during training, the discriminator is fed with some real images, meaning some images from the unlabeled data set that we have access to, and some images which are generated by the generator. And then it is trained such that it outputs, for example, 1. So real can be 1 and fake can be 0. So the discriminator is trained such that it outputs 1 for real images from the unlabeled data set, and it outputs 0 for the generated images. So the discriminator is trained in a completely supervised way. Okay. And the generator is trained so as to fool the discriminator. So the generator is trained so as to produce X images such that the discriminator outputs 1 when it is fed with those images. So both have kind of competing loss here. So these two neural networks compete, and the idea is that at the end of the training, the generator ends up producing images which the discriminator finds difficult to distinguish from the real image. Okay, so this is just what we talked about. And yeah, this is the goal, to convert samples from a simple distribution to those from the real data distribution. Yeah. So what we said before is again written here. So the discriminator is a binary classifier that it always gets an image as input, and it has to produce a y which is 1 or 0. Yeah. And let's say we say that y should be 1 when we have real images, and y should be 0 when the input is g of z. Okay, g being the generator. So now we have a classification problem, a binary classification problem. So we can use, for example, the binary cross entropy loss to train the discriminator. So the binary cross entropy loss is defined like this. So if y is the ground truth label and y hat is the prediction, then the binary cross entropy is defined as basically this formula. Now, if we plug in what we wrote here, so when y is equal to 1, you see that this term will go to 0, right? So we will be left with, and y is equal to 1, so we'll only be left with log of y hat. And we want y to be 1 for real images when the discriminator is fed with real images x. So we want, so this whole term collapses to log of d of x. And then when we feed it images that are generated by the generator, so in this case, d of g of z. So we are feeding to the discriminator the images fed by the images generated by the generator. In this case, we want y to be 0. So this portion of the loss goes away. And this portion of the loss, this term is just 1 minus 0, so 1. And log of 1 minus y hat. So log of 1 minus the prediction of the discriminator. So this binary cross entropy loss boils down to this formula here. So this is the loss that we want to train the discriminator with. Okay, when we feed it real images, they will go in here, and when we feed it generated images, they will go in here. And what's the loss for training the generator? It's basically, okay, before that, it's not exactly what I mentioned here. So we do this with samples, so we need to write it in terms of expectations. That's why I said this is more like an intuitive understanding of what's going on, not strictly correct. But okay, it's very similar to what we discussed, but you need to take expectations over whatever distributions you're talking about. So in this case, x's are sampled from the true distribution px, and z's are sampled from the prior distribution that we have on the latent space. So that's the discriminator loss. And the generator loss is basically the opposite of that, right? So we want the generator to generate images such that the discriminator thinks they are real images. Okay, so it turns out that the generator loss is simply the negative of that, of the discriminator loss. And actually, the first term, the generator has no control over because there is no G appearing here. It's just the discriminator dealing with real images. So this will not matter in this loss function, but just to have the same loss for both the networks with just the opposite sign, let's just write it like this. And then we can write both the losses in one line, meaning we can say that we want to, we have this quantity which we want to minimize with respect to the generator, but maximize with respect to the discriminator. So this is this max min kind of optimization that we have to carry out. Okay, and it turns out that this corresponds to minimizing what is known as a F divergence between the true distribution of images that we have and the distribution modeled by the generator. Okay, so that's about GANs, and if you're interested in looking at more details of these models, I can very highly recommend this video. It was given in a machine learning summer school a few years ago, but it's yeah, it's really very nice. So yeah, you can have a look at that if you're interested. It's about, I think, 2 or 3 hours long, but yeah, especially if you're planning to work on these things, it makes a lot of sense to understand this very nicely. Okay, so this is what we did now. We talked about GANs, and now let's look at finally, in the final part of the lecture, let's look at a few applications of GANs. So if you are reading a bit about this, you know that GANs have really become very popular in the last, I don't know, 5-10 years, not 10, but yeah, 5-7 years. And they're really used quite a bit. And initially there were a number of problems with the training and so on, because you have this min-max thing going on. So it was not very stable, but a number of, a lot of progress has been made on that front, and GANs are basically used really quite a lot in recent years. And there's a survey paper here which talks about that, but we will look at a couple of specific applications. Before that, okay, again, I feel like I keep saying it again and again, but yeah, just stop me if something is unclear, because I just don't want to go through a lot of material. I feel like, it can get foggy after a while. Okay.
I have a question about the input into the GANs. For example, if you want the output to be brain images, what exactly do you need to get brain images? The set, actually, what is the set?
Yes, this is the idea of GANs is to feed in images, or sorry, vectors from a known distribution. Okay, so typically what is chosen is this diagonal noise distribution. So zero mean, identity, covariance, noise. So this is really a vector of whatever 100 dimensions, which is just noise, white noise, and then you feed that to the generator.
Okay. Yeah. Thank you.
Yeah. Okay. So this is one application of GANs, which is data augmentation. So this is where unsupervised learning is used to aid supervised learning. Okay. So supervised learning, again, is the problem of learning from labeled data, so paired data. And here L represents a labeled data set. So let's say we have a small labeled data set of XY pairs. Let's say we have, again, 10 images that we have the labels for. But we know that if we just do training, supervised training with this small data set, we will not do a very good job. So we want to use what is known as data augmentation to expand the training data set. So to come up with more pairs of images, so that we will then train with a larger training data set. Okay. So now we call this generated images and generated label corresponding labels as XG and YG. And then we train on this combined set of training data. And the question is how to generate these pairs of images. Okay. So one way of doing this is to do simple transformations of the images, right? So these are cardiac MRI images. So these are like the ventricles and the myocardium and so on. And this is what we want to segment. So this is, let's say, one of the 10 available images and the corresponding segmentation labels that we have. So what we could do is that we could transform this image. So for example, we could rotate this image 90 degrees, and we know that the segmentation labels should also get rotated 90 degrees. So in effect, what we have is we have one more pair of images that we can plug into the training data, right? Or we could scale the image. Just look at a cropped version, which is, we could change, subsample the image to change its resolution. And then we could do the same for the segmentation label. Again, we have a new pair of training data. Or we could change the contrast of this image by applying some kind of, intensity transformation. In this case, the segmentation label will remain unchanged. So essentially what we're doing is we're using some kind of domain knowledge. For example, we are saying that if the intensity changes slightly, the segmentation labels will not change. So we're using this kind of domain knowledge to come up with new pairs of image labels, which we are going to add into our training data. Okay. So, but these are simple transformations. The question is, can we use unlabeled data? So for example, we have 10 images for which we have the segmentations, but we may have another 100 or 1,000 images, which is just images. We don't have the labels for that. The question is, can we use this additional data set to have an algorithm that produces augmentations in a more sophisticated way? Okay. So, and one way of doing this was proposed in this paper, which says, what I'm going to do is I'm going to start with my labeled image, one of the 10 images, and I'm going to give some noise vector, because this is what GANs do. I'm going to feed these two images, like this image and the noise vector, to a generator network. And I'm going to ask the generator to produce a deformation field. Okay, a deformation field is like at each point in the image, you should output a vector, which tells me that if the vector is so big, I need to deform my image with that vector. So if the deformation vector at this point is, let's say, 4 pixels to the top right, then that pixel will move 4 pixels to the top right in the deformed image. Okay, so what we're doing is we're starting with a labeled image, and we are asking a generator to produce a deformed image. Okay, and we will train a discriminator which will try to say whether the deformed image is a real image or a fake image. Okay, and to know this, the discriminator can be fed with all the 1,000 unlabeled images that we have. So we can say that those 1,000 images are real images, and whatever the generator produces are actually fake images. And we know that in GANs, what happens is after training, the generator starts producing images that look like our pool of unlabeled images, right? So the idea is that hopefully after training for a number of iterations, the generator will start producing deformed images that actually look like the unlabeled images that we had. So for example, the structures of the ventricles may be, may only cover a limited amount of variation in the 10 images that we saw in the labeled data. But by using this large data set of 1,000 unlabeled images, we may be able to generate those other types of shapes which were not present in the labeled data. Okay. And the good thing is that we do this by producing a deformation field, and the same deformation field can be applied to the segmentation labels that we have. So these are only labeled images, right? So we have segmentation labels here corresponding to them. We can apply the same deformation field to the segmentation label, and then we will end up with a deformed image and corresponding segmentation label, which is a pair that can go into our set of training images, right? So what we've done is we've used a GAN to convert a labeled image to look like an unlabeled image, utilizing a large pool of unlabeled images. And we have a mechanism to also convert the corresponding segmentation labels, so that in effect we have a segmentation label for this deformed image as well. Not in effect, we actually exactly have it, right? And then we add this to our training data. And similarly, we can do, so here we did what is known as, here we basically did shape changes because we were producing deformation fields, but we could also produce intensity changes. So for example, we can ask the generator to produce some intensity map, which we will add to the image. So this will produce like a image with a different intensity profile. We will again feed this to a discriminator, which will also get fed with a lot of unlabeled images. So if those unlabeled images have different types of intensity profiles, our generator will try to generate intensity profiles that match the unlabeled images, right? And this is what will happen after training, that the generator will start producing intensity maps such that the generated images start looking like unlabeled images. And in this case, we don't even need to change the segmentation labels because we are just adding some intensity. So the ventricles will remain in the same place. So the segmentation labels will be the same, right? And basically, by doing both these steps, the deformation step and the intensity step, we have a method which can generate new images leveraging an unlabeled data set. And these new images with corresponding label pairs are used as data augmentation to improve the training, right? So this is one application of GANs. And another application that I want to talk about briefly is this thing known as visual feature attribution. So what happens here is that let's assume we are doing classification, okay? And let's assume we are doing Alzheimer's disease classification. So we get an image, MRI image, and of the brain, and we want to say whether this person has Alzheimer's disease or whether that person does not have Alzheimer's disease. Okay, and let's say that we have a training data set of some people having Alzheimer's disease, some people not, and we can train a classifier like this. And one of the criticisms of CNNs is that they are somewhat black box like machines. Like they don't tell us why they make a certain prediction. Okay, so in visual feature attribution, the goal is to understand why a network is producing a certain output. So if it's saying that a certain person has AD, what aspects of the image of the brain are making it say so? Okay, so how do we do this? Yeah, so the goal is to produce like this. So if we know that this person has AD, we want to produce something like a disease effect, meaning that these areas of the brain are slightly smaller or larger as compared to healthy subjects, and these are the effects that are causing the network to believe that this person has AD. Okay, this is kind of the goal of what we want to do. And how do we use GANs to do this? That's as follows. So we start with an image of a patient with Alzheimer's disease. Okay, and we are interested in finding which regions of the brain are responsible for this being an AD image. Okay, so we say, let's start with that image, feed it to a generator network here called M, and ask the generator network to produce like a residual. Okay, so what we are going to do is we are going to ask the generator network to produce some image, which we will add to the input image to produce an image which will be fed to the discriminator. Okay, so it's very simple. It's just a couple of steps. So we pass it to the generator. It produces some image which is added to the actual image, the AD image, to produce the generated image. And the generated image is what is evaluated by the discriminator. Okay. So the discriminator gets this generated image as the fake image and an image of a healthy person as a real image. So because of how GAN training works, ideally what will happen is after the generator has been trained, when we feed an AD image, the generator will produce such a residual image such that when we add these two, this will actually look like a real image. This will actually look like a healthy image, right? So the generator will learn to remove the disease effects such that this becomes like a image of a healthy person, because then the discriminator is happy because, healthy person image is generated and healthy person image was given as the real image while training. Okay. So this is another application of GANs where we can, use them to find out disease effects, which is also very interesting. Okay, so with that, we basically come to the end of the lecture. And this is again a summary. So at the end, we just put another tick here. So for this is an application of GANs, and an additional tick here because we saw another way of how we can use unsupervised learning to deal with cases where we don't have a lot of labeled examples. Okay, so with that, I see that it's exactly 4, and it's also the last slide that I have. So yeah, if there are questions, I'm happy to stay back for another 5-10 minutes. But otherwise, we can basically end the lecture. So you can let me know somewhere. Okay. I just wait for 30 seconds. If there's no question, then you can say bye. Okay, this one. Yeah. Is there an opportunity to join the Slack channel without version email? Huh. Should be possible, no? Are you not able to do it? Yeah, thank you for the thank yous. But I did request a vision email, but I don't think you should need a vision email to join the Slack channel, no? Once you have the invitation link, that should suffice, right? Is there someone else who could join without a vision email? Yeah, I think it should work. Yeah, if not, use it, and you can like write to me via email, and we can sort it out. Okay, so it seems like there are no other questions regarding the material. If there are at a later point, use the Slack channel, or if that's not working, just write to me or Ender, and yeah, best of luck then. Okay, I'm going to end the meeting. Bye.